Black holes occupy a peculiar position in our understanding of the universe, not because they are especially exotic among cosmic phenomena, but because they represent a point where the mathematical frameworks we use to describe reality appear to contradict one another in ways that cannot be easily resolved or dismissed. The question of whether black holes break physics requires first establishing what we mean by physics being broken, and this itself turns out to be a more subtle matter than it might initially appear. Physics as a discipline operates through mathematical models that describe relationships between measurable quantities, and these models are considered successful when they accurately predict the outcomes of experiments and observations. A model does not need to be complete or final to be useful, and the history of physics is largely a history of models that worked extraordinarily well within certain domains while failing or becoming inapplicable outside those domains. Newton's mechanics, for instance, provided an essentially complete description of gravitational phenomena for over 2 centuries before it was recognized that this description became inaccurate at very high velocities or in very strong gravitational fields. The Newtonian framework was not wrong in any practical sense for the problems it was designed to address, but it was revealed to be an approximation of a more comprehensive framework when applied to conditions that Newton could never have tested or even conceived of testing. The development of general relativity in the early 20th century arose precisely from recognizing that Newtonian gravity could not be reconciled with the principle that nothing can travel faster than light. If gravity were an instantaneous force acting across empty space, as Newton's equations implied, then the gravitational influence of a moving object would be felt everywhere in the universe at the same moment the object moved, which would constitute a form of information travelling infinitely fast. Einstein's insight was that gravity could instead be understood as a geometric property of spacetime itself, with mass and energy causing spacetime to curve in ways that affected the motion of other objects. This reconceptualization was not merely a technical adjustment, but a fundamental shift in how physical reality was conceived, replacing the idea of forces acting through space with the idea of objects following the shortest available path through a curved space-time geometry. The mathematical apparatus of differential geometry that Einstein employed had been developed decades earlier by mathematicians with no particular interest in physics, and the fact that these abstract mathematical structures turned out to describe gravitational phenomena with unprecedented accuracy was itself a source of some philosophical puzzlement. The equations of general relativity, when applied to configurations of matter and energy that could be measured or inferred from astronomical observations, gave predictions that matched those observations with remarkable precision, from the slight anomaly in Mercury's orbit that Newtonian mechanics could not explain, to the bending of light by the sun that was confirmed during the solar eclipse of 1919. Yet the same equations, when applied to extreme conditions involving very large masses compressed into very small regions, produced solutions with properties that seemed impossible to interpret physically. The first such solution was discovered by Carl Schwarzschild in 1916, within months of Einstein publishing the field equations of general relativity, and it described the spacetime geometry around a perfectly spherical non-rotating mass. Schwarzschild was serving in the German military on the Eastern Front when he performed these calculations, and he died shortly afterward from an autoimmune disease, probably never fully appreciating the conceptual difficulties that his solution would eventually generate. The Schwarzschild solution contained a surface, now called the event horizon, at a particular radius from the centre of the mass, where certain terms in the equations became infinite, or changed sign in ways that seemed to indicate a barrier of some kind. Inside this radius, the equations predicted that all possible paths through spacetime led inexorably toward the centre, where the curvature of spacetime became infinite. This infinite curvature, concentrated at a single point of zero size, was the singularity, and the entire region from which nothing could escape was what we now call a black hole, although that term would not be coined until the 1960s. For several decades, most physicists regarded these extreme solutions as mathematical curiosities with no physical relevance. The assumption was that no realistic physical process could compress matter sufficiently to create such an object, and that the singularity was an artifact of the perfect symmetry assumed in Schwarzschild's calculation rather than a genuine prediction of the theory. Real stars were not perfectly spherical, the reasoning went, and any small deviation from spherical symmetry would prevent the formation of a true singularity. This assumption was not unreasonable given the state of knowledge at the time, but it turned out to be incorrect. The singularity theorems proved by Roger Penrose and Stephen Hawking in the 1960s demonstrated that singularities were a generic feature of gravitational collapse in general relativity, not an artifact of special assumptions. Under very general conditions involving the concentration of matter and energy, general relativity predicted that spacetime would inevitably develop singular points where curvature became infinite and the equations of the theory ceased to be meaningful. This was a profound result because it showed that general relativity contained within itself the seeds of its own incompleteness, a theory that predicted conditions under which its own mathematical framework broke down was pointing toward the limits of its own validity. The physical interpretation of what actually happens at a singularity remains deeply unclear, and this is one of the central ways in which black holes might be said to break physics, or at least break our current understanding of physics. A singularity in general relativity is not like a physical object located at a point in space. It is more accurately described as a boundary or edge of space-time itself, beyond which the mathematical structure of the theory cannot be extended. Attempting to describe what happens at the singularity using the tools of general relativity is somewhat like attempting to describe what is north of the North Pole using ordinary geography. The question is not that we lack information about what is there, but that the conceptual framework we're using does not have the resources to formulate a meaningful answer. Some physicists have suggested that the singularity should be understood as a limitation of general relativity rather than a feature of physical reality, and that a more complete theory of gravity, one that incorporates quantum mechanical effects, would reveal that the singularity is replaced by something finite and comprehensible. Others have argued that the singularity might be a genuine feature of reality, a place where the usual rules simply do not apply, although what this would mean in practice is difficult to articulate clearly. The event horizon of a black hole presents a different set of conceptual challenges. Unlike the singularity, the event horizon is not a place where the equations of general relativity become singular or undefined. An observer falling through the event horizon of a sufficiently large black hole would not notice anything unusual about the local spacetime geometry at the moment of crossing. The curvature of spacetime at the horizon of a supermassive black hole, such as the one at the centre of our galaxy, would actually be quite gentle by everyday standards, less than the curvature that exists at the surface of the Earth. What makes the event horizon special is not what happens there locally, but what happens globally, meaning the structure of all possible paths through space-time in that region. Once an object crosses the event horizon, all of its possible future trajectories lead deeper into the black hole and eventually toward the singularity. There is no path that leads back out regardless of how fast the object accelerates, or in what direction it attempts to move. Light itself, which follows the fastest possible path through space-time, cannot escape. This is not because some force is pulling the light back, but because the geometry of space-time inside the horizon is arranged such that all directions point inward in a certain technical sense. The global nature of the event horizon creates some of the most puzzling problems in black hole physics. An observer falling into a black hole would not perceive themselves as having crossed any special boundary. They would continue to receive light from objects that were inside the horizon with them. They would continue to experience the passage of time in the normal way, and they would not have any direct evidence that they could not escape until they attempted to do so. An observer remaining outside the black hole, however, would see something very different. Due to the extreme gravitational redshift near the horizon, light escaping from objects falling toward the black hole would be stretched to longer and longer wavelengths, and the time between successive signals would be stretched correspondingly. From the outside, an object falling toward the horizon would appear to slow down asymptotically, taking an infinite amount of time to cross the horizon, while also fading to invisibility as the light it emitted was redshifted beyond detection. These two perspectives, the falling observer who crosses the horizon in finite time, and the distant observer who never sees the crossing occur, are both valid descriptions within general relativity, and the theory provides a consistent way to relate them. But the relationship involves features of space-time that have no analogue in everyday experience, and intuitions developed in ordinary circumstances can be deeply misleading when applied to these extreme situations. The thermodynamic properties of black holes add another layer of complexity to the picture. In the early 1970s, Jacob Bekenstein, then a graduate student, proposed that black holes should be assigned an entropy proportional to the area of their event horizons. This suggestion was initially controversial because it implied that black holes should also have a temperature, and anything with a temperature should emit thermal radiation. But black holes, by definition, were objects from which nothing could escape, so how could they radiate anything? Stephen Hawking initially set out to prove that Bekenstein was wrong, but his own calculations, performed using the framework of quantum field theory and curved spacetime, showed that black holes did indeed emit radiation with a thermal spectrum. The mechanism responsible for this radiation was subtle, and involved the way that quantum vacuum fluctuations were affected by the presence of an event horizon. Near the horizon, pairs of virtual particles that would normally annihilate each other could instead be separated, with one falling into the black hole and the other escaping to infinity. The escaping particles constituted a flux of radiation that carried energy away from the black hole, causing it to lose mass very slowly over time. For stellar mass black holes, this radiation is entirely negligible, with temperatures far below the cosmic microwave background and evaporation times many orders of magnitude longer than the current age of the universe. But for very small black holes, if any exist, the temperature would be high and the evaporation rapid. Hawking radiation revealed a deep tension between general relativity, quantum mechanics, and thermodynamics that has not been resolved after nearly 5 decades of investigation. The problem, known as the black hole information paradox, concerns what happens to the information encoded in the quantum state of matter that falls into a black hole. According to quantum mechanics, the evolution of quantum states is unitary, meaning that information is never truly lost. In principle, if you knew the complete quantum state of a system at one time, you could calculate its state at any other time, either forward or backward. But when matter falls into a black hole, and the black hole subsequently evaporates through Hawking radiation, it appears that the information about the original matter is lost. The Hawking radiation is thermal, meaning it depends only on the mass, charge, and angular momentum of the black hole, not on the details of what fell in. A black hole formed from the collapse of a star would emit exactly the same Hawking radiation as a black hole of equal mass formed from the collapse of an equivalent mass of old shoes or physics textbooks. If the black hole evaporates completely, which according to Hawking's calculation it eventually would, then all trace of the original quantum state would have been erased from the universe, violating the principle of unitarity. Various resolutions to the information paradox have been proposed, and none has achieved universal acceptance. One possibility is that the information is somehow encoded in the Hawking radiation in a very subtle way that is not apparent from the semi-classical calculation that Hawking performed. The radiation might appear thermal when examined at the level of individual quanta, but correlations between the quanta might preserve the information in an encrypted form that could, in principle, be decoded by a sufficiently powerful observation. This resolution would require modifications to our understanding of how information behaves near the event horizon, and some proposals along these lines have suggested that the interior of the black hole might not exist in the way that classical general relativity describes. Another possibility is that the evaporation process does not go to completion, and a stable remnant containing the information is left behind. This remnant would have to be very small and very long-lived, and the information would effectively be removed from the observable universe even if it were not destroyed. A third possibility, suggested by Hawking himself in later work, is that information might be able to escape from the black hole through subtle quantum gravitational effects that are not captured by the semi-classical approximation. The various proposals differ not just in their technical details but in their implications for fundamental physics, and the debate has stimulated an enormous amount of research at the interface of general relativity, quantum field theory, and quantum information theory. The fact that this problem remains unresolved reflects the deeper difficulty of constructing a theory that consistently incorporates both general relativity and quantum mechanics. These two frameworks are the pillars of modern physics, each extraordinarily well confirmed within its domain of applicability, and yet they appear to be incompatible when applied simultaneously to the same phenomena. general relativity treats spacetime as a smooth, continuous geometric structure whose curvature is determined by the distribution of matter and energy. Quantum mechanics treats matter and energy as composed of discrete quanta, whose properties are described by probability amplitudes that evolve according to the Schrödinger equation or its relativistic generalizations. When quantum mechanical matter is placed in a fixed, curved spacetime background, the resulting quantum field theory in curved spacetime produces sensible and testable predictions, including the existence of Hawking radiation. But when the spacetime geometry itself is treated as a dynamical quantum variable, subject to quantum fluctuations and superposition, the standard techniques of quantum field theory produce infinities that cannot be removed by the usual renormalization procedures. General relativity, unlike the other fundamental forces, is not renormalizable, meaning that it cannot be converted into a consistent quantum theory using the methods that work for electromagnetism and the strong and weak nuclear forces. This incompatibility is not necessarily surprising from a historical perspective. General relativity was developed before quantum mechanics was fully formulated, and Einstein himself was never entirely comfortable with the probabilistic nature of quantum theory. The conceptual foundations of the two theories are quite different, with general relativity describing a deterministic geometric evolution of spacetime and quantum mechanics describing a probabilistic evolution of state vectors in an abstract Hilbert space. Attempts to combine them have taken various forms over the past several decades, with string theory and loop quantum gravity being the most extensively developed approaches, but none has yet produced a complete and experimentally verified theory of quantum gravity. Black holes are particularly important in this context, because they are among the few physical situations where quantum gravitational effects are expected to be significant. At the singularity, the curvature of spacetime reaches the Planck scale, where the quantum fluctuations of geometry should be comparable to the classical geometry itself. The event horizon, while not involving Planck scale physics directly, is where the global structure of spacetime creates the conditions for Hawking radiation, which is a quantum effect produced by classical gravity. Understanding black holes fully will almost certainly require a theory of quantum gravity, and conversely, any candidate theory of quantum gravity must be able to reproduce the known physics of black holes while resolving the outstanding paradoxes. The observational status of black holes has changed dramatically over the past few decades, and this is relevant to the question of whether they break physics, because it establishes that these objects genuinely exist and are not merely theoretical constructs. For most of the history of black hole research, from Schwarzschild's solution in 1916 through the theoretical developments of the 1970s, black holes were hypothetical objects whose existence was inferred from the dynamics of visible matter or the properties of energetic phenomena near galactic centers. The argument for their existence was strong but indirect. Certain astronomical observations were difficult to explain without invoking an extremely compact, massive object that did not emit light, and a black hole was the only known candidate that fit the requirements. X-ray binary systems, in which a visible star orbited an invisible companion and transferred mass onto an accretion disk that emitted copious X-rays, provided some of the earliest strong evidence. The orbital parameters of these systems indicated that the invisible companion was too massive to be a neutron star, which has a maximum mass determined by the balance between gravitational collapse and neutron degeneracy pressure. The rapid variability of the X-ray emission indicated that the emitting region was very small, consistent with the inner edge of an accretion disk orbiting close to the event horizon of a black hole. The center of our own galaxy provided another line of evidence. Observations of stars orbiting the galactic center, made possible by infrared telescopes that could peer through the intervening dust, revealed that these stars were moving at extraordinary speeds on very tight orbits around an invisible object. By tracking the positions of these stars over many years, astronomers constructed a precise model of their orbits and determined that they were orbiting an object with a mass of about 4 million solar masses concentrated within a region smaller than our solar system. The only known object that could have such a large mass in such a small volume without being visible was a supermassive black hole. More recently, the Event Horizon Telescope, a global network of radio telescopes linked through very long baseline interferometry, produced direct images of the immediate vicinity of the supermassive black holes at the centres of the galaxy M87 and our own Milky Way. These images showed the characteristic shadow cast by the event horizon, a dark region surrounded by the bright emission from superheated gas in the accretion disk. While the images did not show the event horizon itself, which is a mathematical surface rather than a physical object, they showed light that had passed very close to where the horizon should be, according to general relativity. And the size and shape of the shadow matched the predictions of the theory with impressive accuracy. The detection of gravitational waves by the LIGO and Virgo collaborations beginning in 2015 provided yet another form of evidence for black holes and a direct test of general relativity in the strong field regime. When two black holes orbit each other, they emit gravitational waves, which are ripples in the fabric of spacetime that propagate outward at the speed of light. As the black holes lose energy to gravitational radiation, they spiral closer together, orbiting faster and emitting stronger waves until they eventually merge into a single larger black hole. The final stages of this process produce a characteristic signal, a chirp that rises in frequency and amplitude until the moment of merger, followed by a ring down as the newly formed black hole settles into a stable configuration. The detected signals match the predictions of numerical simulations based on general relativity with remarkable precision, providing strong confirmation that the theory correctly describes the behaviour of spacetime, even in the most extreme conditions accessible to observation. The ring-down phase was particularly informative because the frequencies and damping times of the oscillations depend on the mass and spin of the final black hole in a way that is predicted by general relativity. If general relativity were incorrect, the ring-down frequencies would differ from the predictions, and no such discrepancy has been observed. These observations confirm that black holes exist and that general relativity accurately describes their behaviour at the macroscopic level, but they do not directly probe the regimes where the theory is expected to break down, or where quantum effects should become important. The singularity at the centre of a black hole is hidden behind the event horizon, from which no information can escape, so it cannot be observed directly. The Hawking radiation from astrophysical black holes is far too weak to detect with any foreseeable technology. The quantum gravitational effects that might resolve the information paradox or modify the classical structure of the event horizon are expected to operate at scales far smaller than anything that can be probed by current or planned experiments. In this sense, the most fundamental questions about black holes remain unanswerable by observation, at least for now. We can confirm that black holes behave as general relativity predicts in the observable regime, but we cannot test the predictions of the theory in the unobservable regime, and we cannot determine whether the paradoxes that arise in that regime represent genuine breakdowns of physics or merely limitations of our current theoretical understanding. The concept of what it means for physics to break requires further clarification at this point. One way to interpret the question is to ask whether there are situations where the mathematical frameworks of physics produce no predictions at all, or produce predictions that are logically inconsistent. By this criterion, the singularity of a black hole might be said to break physics because the equations of general relativity become undefined there. The theory cannot predict what happens at or beyond the singularity, because the mathematical structure of the theory does not extend to that point. But this interpretation may be too strong, because it treats the mathematical framework as if it were identical to physical reality, rather than a model of physical reality. A model that becomes inapplicable in certain extreme conditions is not necessarily wrong, it may simply be incomplete. Newtonian mechanics becomes inapplicable at velocities close to the speed of light, but we do not say that Newtonian mechanics is broken. We say instead that it is an approximation that works well at low velocities and must be replaced by a more comprehensive theory at high velocities. Similarly, general relativity may be an approximation that works well at large scales and low curvatures, and must be replaced by a more comprehensive theory at small scales and high curvatures. The singularity may be indicating not that physics itself breaks down, but that general relativity reaches the limit of its domain of validity. Another way to interpret the question is to ask whether there are situations where different well-established principles of physics conflict with each other, producing contradictory predictions about the same phenomena. By this criterion, The black hole information paradox might be said to indicate a breakdown of physics because general relativity, quantum mechanics, and thermodynamics appear to make incompatible demands. General relativity says that information falls into the black hole and reaches the singularity. Quantum mechanics says that information cannot be destroyed because quantum evolution is unitary. Thermodynamics says that black holes have entropy and therefore contain information proportional to their surface area, which decreases as the black hole evaporates. These statements cannot all be true in their naive interpretations, so at least one of them must be modified or abandoned. The resolution of this paradox would reveal which of our current principles is approximately rather than exactly true, or would require a reconceptualization of one or more of them in a way that allows them to coexist. This type of apparent breakdown is not necessarily a failure of physics, but can be a signpost pointing toward new physics, indicating the direction in which our understanding needs to be extended or revised. A third way to interpret the question is to ask whether black holes involve phenomena that are fundamentally beyond the capacity of any physical theory to describe, not because our current theories are incomplete, but because the phenomena exceed the limits of what can be captured in mathematical or conceptual terms. This is a more philosophical interpretation, and it raises questions about the nature of scientific knowledge and its relationship to reality. Throughout the history of physics, phenomena that once seemed mysterious or inexplicable have eventually been brought within the scope of theoretical understanding, and there is no strong reason to believe that this process will not continue. But it is also possible that some aspects of reality are genuinely beyond human comprehension, not because of any practical limitation, but because of a fundamental mismatch between the structure of reality and the structure of human cognition. Black holes, with their one-way horizons, their singularities hidden from observation, and their apparent violations of cherished physical principles, might seem like candidates for this type of fundamental unknowability. But such a conclusion would be premature, and most physicists working on these problems proceed on the assumption that a comprehensible theory is achievable even if it has not yet been found. The history of attempts to construct a theory of quantum gravity illustrates both the difficulty of the problem and the variety of approaches that have been tried. String theory, which emerged in the 1970s as a candidate theory of the strong nuclear force before being reconceived as a theory of gravity, proposes that the fundamental constituents of matter are not point particles, but tiny, one-dimensional strings, whose vibrational modes correspond to different particles. In string theory, the graviton, the hypothetical quantum of the gravitational field, appears naturally as one of the vibrational modes, and the theory is believed to be consistent at all energy scales, avoiding the infinities that plague attempts to quantize general relativity directly. String theory also predicts the existence of extraspatial dimensions beyond the three we observe, which must be compactified or curled up on scales too small to detect. The mathematical structure of string theory is extraordinarily rich, and it has produced many insights into the behavior of black holes, including calculations of black hole entropy that match the Beakenstein-Hawking formula and provide a microscopic explanation for where the entropy comes from. In certain special cases, involving black holes with particular charges and embedded in particular geometries, string theory provides a complete description of the quantum states of the black hole and demonstrates explicitly that information is preserved in the evaporation process. However, string theory also has significant limitations as a solution to the problem of quantum gravity. The special cases for which calculations can be performed do not include the astrophysical black holes that we actually observe, which are uncharged and embedded in a four-dimensional spacetime that does not resemble the highly symmetric configurations amenable to calculation. The predictions of string theory that differ from those of general relativity or the standard model of particle physics are expected to become apparent only at energy scales far beyond what any experiment can achieve, making the theory extremely difficult to test. And string theory is not a single theory, but a vast landscape of possible solutions, each corresponding to a different way of compactifying the extra dimensions, and there is no known principle that selects which solution describes our universe. These limitations do not mean that string theory is wrong, but they do mean that it has not yet achieved the status of a confirmed physical theory. It remains a mathematical framework of great beauty and power, whose physical relevance is still being explored. Loop quantum gravity takes a different approach, attempting to quantize the space-time geometry directly rather than embedding gravity in a higher dimensional string framework. In loop quantum gravity, space-time at the smaller scales is not a smooth continuum, but a discrete network of quantum states, with areas and volumes taking on discrete values much as energy levels do in atomic physics. The singularity at the center of a black hole is replaced in this framework by a quantum region, where the classical description breaks down but the quantum description remains finite and well-defined. Some calculations in loop quantum gravity suggest that the singularity might be replaced by a quantum bounce, in which the collapsing matter reaches a maximum density and then expands again, possibly into a new region of space-time that is causally disconnected from the original universe. These results are intriguing but preliminary, and loop quantum gravity faces its own challenges in recovering the smooth classical space-time of general relativity in the appropriate limit and in making contact with the other forces and particles described by the standard model. Like string theory, it is a research program in progress rather than a completed theory. The nature of space and time themselves is called into question by the study of black holes, and this is perhaps the deepest sense in which black holes might be said to break physics, or at least break our intuitive understanding of what physics describes. In general relativity, space-time is a dynamical entity that responds to the presence of matter and energy, curving and warping in ways that are described by Einstein's field equations. But space-time is also the arena in which all physical processes take place, the background against which particles move and fields propagate. When space-time itself develops singularities or horizons that prevent information from escaping, the distinction between background and dynamics becomes problematic. A complete theory of quantum gravity may require abandoning the concept of space-time as a fundamental entity and reconstructing it as an emergent phenomenon arising from more primitive ingredients. The holographic principle, proposed by Gerardus Hooft and developed by Leonard Susskind, suggests that the fundamental degrees of freedom of a region of space-time may not be distributed throughout the volume of that region, but may instead live on the boundary, encoded in a lower dimensional structure that somehow gives rise to the appearance of the higher dimensional interior. This principle was made precise in the context of string theory by Juan Maldazzina's discovery of the SCCFT correspondence, which establishes an exact equivalence between a gravitational theory in a negatively curved space-time and a non-gravitational quantum field theory living on the boundary of that space-time. The implications of this correspondence for black holes are profound, because it suggests that the physics of a black hole interior might be completely described by degrees of freedom on the exterior, which would resolve the information paradox by showing that information is never really inside the black hole in the fundamental description. These developments have led some physicists to propose that the very concepts of space and time are not fundamental, but emerge from more basic quantum mechanical structures. If this is correct, then questions about what happens inside a black hole may not have the form we naively expect. There may not be an inside in the traditional sense, or the inside may be a reconstructible from exterior data in a way that does not involve the usual notion of spatial location. Such proposals are highly speculative and far from being experimentally testable, but they indicate the depth of the conceptual revision that might be required to fully understand black holes. The classical picture of a black hole as a region of space from which nothing can escape may be approximately correct for macroscopic observations, while being fundamentally misleading about the microscopic reality. The relationship between observation and existence is also complicated by black holes in ways that touch on foundational issues in the philosophy of physics. The event horizon is defined by the behavior of light rays over the entire future history of the space-time, which means that determining whether a particular surface is near event horizon requires knowledge of events that have not yet occurred. This is in principle no obstacle to the mathematical definition, but it raises questions about the physical reality of the horizon in the present moment. Some physicists have argued that the event horizon should be replaced by a quasi-local concept, such as the apparent horizon, which can be determined by local measurements, and does not depend on the future evolution of the space-time. The distinction matters for questions about what an observer falling into a black hole actually experiences, and whether the dramatic effects associated with the event horizons are physical or merely definitional. Similarly, the singularity at the center of a black hole is not directly observable because it is hidden behind the event horizon, and the cosmic censorship conjecture proposed by Roger Penrose suggests that this is a general feature of gravitational collapse. Singularities are always hidden inside horizons and can never be observed from outside. If cosmic censorship is true, then the breakdown of physics at the singularity is quarantined and does not affect the rest of the universe. If it is false, and naked singularities can form, then the breakdown would be visible and the predictive power of physics would be genuinely compromised. The question of whether black holes break physics thus depends on what aspects of black holes one focuses on and what standards one applies to the concept of breaking. At the level of observations and predictions within the domain where general relativity is well tested, black holes do not break physics at all. They are objects whose existence is inferred from solid evidence, whose properties are described by well-confirmed equations, and whose behavior in the observable regime matches theoretical predictions with high precision. At the level of fundamental principles and the interface between gravity and quantum mechanics, black holes reveal tensions and paradoxes that current physics cannot fully resolve. Whether these tensions represent a genuine breakdown or merely a signpost toward future developments remains to be seen. The history of physics suggests that such tensions are often resolved by conceptual advances that preserve the valid insights of the previous frameworks while extending their domain of applicability. The resolution of the black hole information paradox, if and when it comes, will likely involve new insights about the nature of information, gravity and spacetime that we cannot currently anticipate, but that will seem natural and even inevitable in retrospect. The role of black holes in the broader context of astrophysics and cosmology is also worth considering when evaluating their relationship to physics as a whole. Black holes are not isolated anomalies but integral components of the cosmic ecosystem. Stellar mass black holes are the endpoints of massive star evolution, forming when the core of a star exhausts its nuclear fuel and collapses under its own gravity. The collapse is halted for smaller stars by electron degeneracy pressure or neutron degeneracy pressure, producing white dwarfs or neutron stars, but for cores above a certain mass, no known force can halt the collapse and a black hole is the result. The boundary between neutron stars and black holes depends on the equation of state of ultra-dense nuclear matter, which is not fully understood, and observations of neutron stars and black holes in binary systems are gradually constraining the possibilities. Supermassive black holes found at the centers of most large galaxies, including our own, are millions to billions of times more massive than the Sun and play a significant role in galaxy formation and evolution. The energy released by matter falling into these black holes powers the most luminous phenomena in the universe, including quasars and active galactic nuclei, and the feedback from these phenomena affects the rate at which stars form in the surrounding galaxy. There is evidence of correlations between the mass of a galaxy's central black hole and the properties of the galaxy itself, suggesting that the growth of black holes and the growth of galaxies are linked in ways that are still being understood. The extreme conditions near black holes also make them unique laboratories for testing physics, under circumstances that cannot be reproduced on Earth. The accretion disks around black holes reach temperatures of millions of degrees and produce radiation across the electromagnetic spectrum, from radio waves to gamma rays. The dynamics of plasma in these disks are governed by magnetohydrodynamics and general relativity in combination, and understanding the observed properties of these systems requires sophisticated numerical simulations that solve the equations of both frameworks simultaneously. Jets of relativistic particles are often observed emerging from the vicinity of black holes, accelerated by mechanisms that are still debated but probably involve the extraction of rotational energy from the black hole itself through the interaction with magnetic fields. These jets can extend for millions of light years and affect the evolution of the intergalactic medium. The study of these phenomena connects black hole physics to a vast range of astrophysical processes and makes black holes central objects in our understanding of the universe rather than marginal curiosities. The history of black hole research also illustrates broader themes about how scientific knowledge develops and how theoretical predictions are eventually tested. The mathematical possibility of black holes was recognized almost immediately after general relativity was formulated, but the physical reality of these objects was doubted for decades. The theoretical work of the 1960s and 1970s, including the singularity theorems, the area theorem, and the discovery of Hawking radiation, established the conceptual framework for understanding black holes, but did not produce direct observational evidence. The observational evidence accumulated gradually through the late 20th century, beginning with X-ray binaries and culminating in the Event Horizon Telescope images and gravitational wave detections of the 21st century. Each new line of evidence confirmed the predictions of general relativity, while leaving the deepest theoretical questions unresolved. This pattern, in which theoretical predictions are made long before they can be tested and are eventually confirmed while raising new questions, is characteristic of physics at the frontier and reflects the interplay between mathematical reasoning, physical intuition, and experimental ingenuity that drives the field forward. The question of whether black holes break physics can also be approached from the perspective of what physics is supposed to do. If the purpose of physics is to describe and predict the phenomena we can observe, then black holes do not break physics because the observable phenomena associated with black holes are well described by our current theories. If the purpose of physics is to provide a complete and consistent account of reality at all scales and in all conditions, then black holes reveal that our current theories are incomplete, though not necessarily broken in the sense of being wrong or useless. The distinction matters because it affects how we should respond to the challenges that black holes present. If black holes simply mark the edge of the known world, beyond which our maps do not extend, the appropriate response is to develop better theories that extend the map. If black holes involve genuine paradoxes or contradictions, the appropriate response might be to revise the logical or conceptual foundations on which our theories are built. The evidence currently favours the first interpretation. Black holes reveal the limits of general relativity and call for a theory of quantum gravity, but they do not appear to involve logical contradictions that would undermine the scientific enterprise itself. The ongoing research into black holes spans a remarkable range of disciplines and techniques, from mathematical physics and quantum information theory to numerical relativity and observational astronomy. The cross-fertilization between these fields has been one of the most productive aspects of black hole research, with insights from one area often suggesting new approaches in another. The Bekenstein-Hawking entropy formula, for instance, links the thermodynamics of black holes to the geometry of their event horizons, and this link has inspired the holographic principle and the search for a microscopic theory of black hole entropy. The information paradox has brought quantum information theorists into the conversation, leading to new concepts like the firewall, which is a hypothetical phenomenon at the horizon that would destroy any object attempting to cross, and the proposal that the interior of a black hole might be maximally entangled with the exterior in a way that creates paradoxes for any observer who attempts to describe both. The ER-EPR conjecture, proposed by Maldacena and Susskind, suggests that wormholes, solutions of general relativity that connect distant regions of spacetime, and quantum entanglement are fundamentally the same phenomenon, a proposal that would unify spacetime geometry and quantum correlations in a radical way if it could be made precise. These ideas are at the cutting edge of current research and illustrate the fertility of black holes as a stimulus for new physics. The philosophical implications of black holes have also attracted significant attention, with philosophers of physics examining questions about the nature of spacetime, the meaning of singularities, and the interpretation of quantum mechanics in the presence of gravity. The problem of time in quantum gravity, for instance, arises because general relativity treats time as a dynamical variable that participates in the physics, while quantum mechanics treats time as a fixed background parameter that labels the evolution of quantum states. Reconciling these two treatments requires a new understanding of what time is and how it relates to observable quantities, and black holes, where the curvature of spacetime becomes extreme and the notion of time inside the horizon is transformed, provide a concrete context for exploring these issues. The debate about whether the interior of a black hole really exists, or whether it should be understood as an emergent or reconstructed entity from exterior data, touches on foundational questions about the relationship between theoretical descriptions and physical reality. The cultural and popular significance of black holes is also notable, although this is somewhat tangential to the scientific questions. Black holes have captured the public imagination as few other scientific concepts have, appearing in science fiction, art, and popular culture as symbols of mystery, danger, and the unknown. This cultural fascination reflects the genuine strangeness of black holes, which violate common sense intuitions about space, time, and causality in ways that are both disturbing and fascinating. The images from the Event Horizon Telescope were widely covered in the media and generated enormous public interest, demonstrating that the appetite for genuine scientific discovery remains strong even when the technical details are challenging to communicate. This public interest is an asset for the scientific community, as it helps to sustain support for fundamental research and inspires new generations of scientists. But it also creates challenges, as the popular understanding of black holes is often shaped by inaccurate or sensationalized accounts that can obscure the genuine scientific issues. Returning to the central question of whether black holes break physics, the most accurate answer is probably that black holes expose the seams where our current physical theories meet their limits. General relativity predicts the existence of singularities, where its own equations become meaningless, indicating that the theory is incomplete. Quantum mechanics, applied to the vicinity of black holes, produces the Hawking radiation and raises the information paradox, indicating that quantum mechanics and general relativity cannot both be exactly correct in their current formulations. Thermodynamics, applied to black holes, yields the Bekenstein-Hawking entropy, which suggests that the fundamental degrees of freedom of gravity are related to surfaces rather than volumes, indicating that our understanding of spacetime may need to be radically revised. These are not signs that physics is broken in the sense of being wrong or incoherent, but signs that physics is incomplete in the sense of not yet having achieved a unified framework that encompasses all phenomena. The incompleteness is not a failure but a frontier, and the exploration of this frontier is one of the central challenges of contemporary physics. The future of black hole research is likely to involve both theoretical advances and observational breakthroughs. On the theoretical side, the development of a consistent theory of quantum gravity, whether through string theory, loop quantum gravity, or some other approach, would resolve many of the outstanding questions about black holes and reveal what replaces the singularity, how information is preserved, and how the interior of a black hole is related to the exterior. On the observational side, improvements in gravitational wave detectors will enable the detection of black hole mergers at greater distances and with higher precision, testing general relativity in new regimes, and potentially revealing signatures of quantum gravitational effects. The next generation of Event Horizon Telescope observations may provide more detailed images of the regions near black hole horizons, testing predictions about the behavior of light and matter in strong gravitational fields. Space-based gravitational wave detectors, currently in the planning and development stages, would be sensitive to mergers involving supermassive black holes, opening a new window on the most extreme gravitational phenomena in the universe. The question of whether black holes break physics will ultimately be answered by the progress of physics itself. If a unified theory emerges that consistently describes black holes at all scales and resolves the outstanding paradoxes, then black holes will not have broken physics, but will have guided it toward deeper understanding. If no such theory proves possible, and the paradoxes persist despite our best efforts, then we may have to consider more radical conclusions about the limits of physical knowledge. But the history of physics gives a reason for optimism. Puzzles that seemed intractable to one generation have often been resolved by the next, and the apparently paradoxical features of black holes may similarly yield to new insights that we cannot currently anticipate. The exploration continues, driven by the same combination of mathematical imagination, physical intuition, and observational ingenuity that has characterized physics from its origins. Black holes remain among the most fascinating objects in the universe, not because they break physics, but because they push physics to its limits and beyond, illuminating the boundaries of what we know and the possibilities of what we might yet learn.